Hey guys, welcome back to another Advanced Procrastinators and Prep B collaboration physics tutorial video. This is a quick lesson for the entire unit of momentum and impulse. You can apply this to AP Physics 1, and you can also apply it to Physics 30-1, which is a North American, specifically Canadian curriculum. Let's get started. So we have our usual disclaimers. These are created for AP Physics 1 as a base. However, I did say we can touch upon 30-1 material as well. Now, before you watch the rest of this video, please make sure you know Newton's second law, the law of conservation of energy, and about kinetic energy, because we will be discussing those in the next slides. So before we get started, of course, here's a quick hello from the people who bring you this video. My name's Alex, and I'm the one going through the physics series with you guys. And Esther is the fantastic human being who has done all the practice problems you'll see in this video. All right, table of contents, let's go. First of all, we're gonna go start with an intro to kinetic energy, just a little review, and touch upon inertia. So this will be the entire intro to momentum. Then we'll go on to impulse, which is talking more in depth about the law of conservation of momentum and how it relates to impulse, what exactly impulse is, and how we apply it. The last thing we'll be doing is 1D and 2D collisions. 1D collisions you will most definitely see on the AP Physics 1 test. 2D collisions is a little bit of an extension. However, it really is a small branch off of 1D collisions, so there's not a lot of differences in that. Now, this here says deriving Newton's second law using momentum. However, we're not really deriving, we're only going to be using it in scenarios. So, of course, practice problems as we go. Let's get started. Kinetic energy and inertia. Scroll a bit faster. So, inertia is the property of an object. Inertia is the property of an object to stay in rest or motion. And kinetic energy, as we should know, is the amount of energy that an object possesses due to motion. Motion, because we know that for kinetic energy, we have EK equals 1/2 mass times velocity squared. So it must be in motion. Now, inertia is not an actual formula or variable. It's just the property of an object. The property of an object to stay in rest or motion. So momentum is the combination of these two concepts. And what we do for momentum is the formula here. We have P equals mv, and I wrote it all lowercase here. This is what we'll write it mostly as. The text here is uppercase, but they're the same. So P is momentum. Momentum. M is mass. We mostly write mass in kilograms, and velocity here, or speed, in meters per second usually. Velocity or speed, because speed is just velocity with a direction. So what this tells us is that, let me move this to the side here. What this tells us is that momentum we measure in kilogram meters per second. So, how do we apply this? Well, first we have to know two important concepts here. Energy, kinetic energy or all energy, changes form in different scenarios, and the total energy is never lost, never. It depends on the size of the system you're looking at. For example, you may say, okay, well, a projectile might lose energy due to friction if it's going against a surface or air friction. Well, the energy is still conserved within our isolated system of Earth. If we were to do this in a lab, perhaps on an air table, then you would be narrowing down the isolated system and trying to make it near perfect so there's no visible change in energy. Now, momentum is always conserved. Always. Momentum is never lost in any way. Momentum doesn't really change. It goes from one object to another. So that's a good point to write down here. It can be transferred, same as energy, from one object to another. And I will go into great detail about this in our next slides. Let's go for a practice problem first, though. This is relatively simple. Motorcycle has a momentum of 24 kilogram meters per second. What would its momentum be if it had twice the mass and the same velocity? Well, we know our basic formula. Let me write it up here. So for this scenario here, we would have the momentum equals twice the mass times the velocity. Now, because this is just a simple multiplication relationship, it doesn't really matter if the 2 is multiplying the m or the v, because it's just multiplication. It doesn't really matter. The order doesn't really matter. So we can see that if mass and velocity, if they're multiplied by a number, here it's 2, that means momentum must go up by 2. So momentum must double. And the same applies to here. Twice the velocity and the same mass, we would have same scenario. Now the next one here, twice the velocity and the same mass, well, you would write it as P equals 2 Vm, and it's the same scenario as up there. Now what if it had half the mass and 4 times the speed? So P equals half the mass times 4 times the speed. Well, again, it's a simple multiplication relationship. So the half and the 4 will work together to create a 2, which means same scenario. Now we have a different one here. If we have triple the mass and half the speed, so we have P equals 3m. So we have P equals 3m times half the speed. Well, we can see here, the 3 and the 1/2, 3 times 1/2 is 1.5. So this scenario here, triple the mass and half the speed, we would have P equals, oh, that is a terrible 3. Sorry about that. 3m times half the speed. We can see the relationship between the 3 and the half will give us 3 out of 2, which means this is the rate, or 1.5, 1.5, is the rate that momentum increases by. Perfect. So this is the simplest momentum equation, P equals mv, and we also have different versions of it. We can have momentum equals m change in v, and with the change in v, the delta v, what it means is momentum equals mass, because you can't have a change in mass. We're not at that level of physics yet. We have a set mass, and we have the final velocity minus the initial velocity. Simple as that. You'll mostly see m delta v on your formula sheets. Now moving on to impulse. There's only really one idea here. Impulse is extremely simple. It's just a change in momentum. So whenever you see delta p, that's impulse. And really what that means, of course, every time we see a delta, is the final momentum minus the initial momentum. Now, oftentimes, when you say impulse, the question actually means force and time. That's the variables they give you. And so that gives us another formula here, which is F net times the change in time equals impulse. And there's no variable for impulse, although we did say you can use change in momentum. Now, F net, of course, is the net force, right? So we have ma And we have change in time. Actually, let me write this here. Net force. And we have change in time. And this is usually in seconds. Net force is usually in newtons. And of course, our impulse could be measured in Newton. Oh, that is not an N. In Newton seconds. North, east, south, and west. You need to start remembering vector directions, and this will come into help when we go with our 1D and 2D collisions. Now, oftentimes when you work with vectors, we give them positive and negative directions because of opposing values. So if we had perhaps an impulse going this way from the west, and we had a slightly smaller impulse coming from the same place from the east, the larger impulse here would effectively end up, and how you would add these up is simply, let's say if west was this direction was positive and this direction was negative. Sign conventions, you can make them up yourself. It doesn't always have to be north and east is positive, south and west is negative, as long as you define it in your question. So here what we would do is take the positive and add, or in this case subtract now, the value. We would end up with the net impulse, which would be still going west. Oh, that is not an arrow. Still going west. There we go. Perfect. And when we remember vectors, we need to remember the x and y coordinates of them. So if I had an impulse going here, and perhaps let's say this is 25 degrees, then we would have an impulse going in the x direction and an impulse going in the y direction. So let's say this is px, this is py, and this would make up our resulting momentum or impulse. And really, in most of these cases, and basically all of these cases, it will be a right angle triangle as a vector. And we will have the Pythagoras theorem that we can use. So px squared plus py squared equals p res squared. And so all our general vector laws apply to here. Let's go with the practice problem. A 0.14 kilogram baseball, initially traveling at 2 meters per second, is hit by a bat in the same direction of travel for 0.05 seconds and accelerates to 4.3 meters per second. Calculate the impulse that the baseball experiences. Well, before we do anything, of course, every single time, list down your variables. So we have mass at 0.145 kilograms. We have our initial velocity is 2 meters per second. It's hit by a bat in the same direction of travel, so we don't have to really worry about our vectors or anything subtracting here. Same direction of travel for 0.05 seconds, and it accelerates, so our final velocity is 4.3 meters per second, and now we know we have a time value of 0.05 seconds. So which one of our momentum formulas should we use? Well, we have our m and our v's, so we could do the impulse, so the momentum is impulse, equals m delta v, which means we have mass times the final velocity minus the initial velocity. So we would have, the answer would be 0.145 kilograms multiplied by 2.3 meters per second, and that would equal, let me grab my calculator right here, and hopefully you've already punched this into yours, is 0.3335 kilogram meters per second. And we need to look at our significant digits. The lowest significant digits is 2 meters per second. which means our answer should round to 0.3 kilogram meters per second. Now what we do have is a change in velocity, which means we should be able to calculate an acceleration, use the acceleration and mass for net force, and then multiply that by the time to use our other formula and see if we get the same answer. So let's do that right now. Let me clear this away. We know our first answer that we got was 0.3 kilogram meters per second. Let's see if we can do that with the impulse equals F net delta t equation. Okay, well, we don't know what our F net is. We know what our delta t is. So we have to calculate F net equals ma, and a equals v over t. And because we have our change in v, yes, we have our change in v and our change in t, then we know that this is again 2.3 meters per second over 0.05 seconds. So what we're really doing is multiplying 2.3 and so if you punch that into your calculator, you would see that we would get an answer of 46 meters per second squared. Now we know that, let's multiply it by our mass, which is 0.145 kilograms, giving us the F net of 6.67 newtons. Now we can do F net delta t. We multiply 6.67 by 0.05 again, and that gives us the same answer. That gives us the answer of 0.3335, and again we can round that to 0.3 kilogram meters per second. So both of these formulas work in the same way. It just depends on the variables you're given and which one would be most efficient and better and simpler for you to understand. Let's move on to 1D and 2D collisions. There are three formulas we can use when we say collisions. We can say there's one for elastic collisions, there's one for inelastic collisions, and there's one for explosions. So let's write all of these down. So elastic. Now remember, elastic collisions, and hopefully you know this from energy, and if you don't, please go back and watch the energy video where I do explain elastic and inelastic. We use the momentum formula m1v1 plus m2v2 equals m1v1 final plus m2, I forgot to put the one here, v2 final. And so what we're saying is that the initial masses traveling at the initial velocity, so the initial momentums, the initial momentum, the sum of the initial momentum is the same as the sum of the final momentum of two objects. And you can go 3 objects, 4 objects, just follow the same format here. So for inelastic collisions, let's write this down, inelastic collisions. Oh, that is what the frick am I doing? Collisions. We have m1v1 plus m2v2 equals m1 plus m2 v final. V final differs from these two velocities there. Now, remember, inelastic collisions is when oftentimes we say they travel together, the 2 or 3 or 4 or however many, the more than one, they travel together, they stick together, and that's why we have our masses combined and summed at the end. So again, the initial sum of the momentum is equal to the final momentum. And then our last one here is for explosions. Explosions. And the best example we can think of here is for bombs. Bombs, they are one mass that can shatter into different other masses. So it's really the inverse, the same, I guess you could say, of inelastic collisions. We just start with the combined mass and velocity, except that now we know it's the initial velocity. And when it explodes, it's still the sum of the momentum of each fragmented piece. So we can actually call this V1. Don't call this V1F. Actually, I'm going to give this a better variable. Let's go with MA. VA. And we'll change these to A and B so we don't get it confused. Plus MB VB. Perfect. Now, these are for 1D collisions. We'll picture that real soon. Now, for 2D collisions, which I did say, which I showed you the X and Y components a couple minutes ago, we use the same 3 formulas, except we break down the vector components even further, again with the X and Y components. So here's a problem with a bomb. A 25-kilogram bomb, initially traveling at 5.4 meters per second, explodes into 3 fragments according to the following data. There's our data right there, and it says to find the speed of a mass C, fragment C. And the thing here, this one's relatively easy because it did not tell us the velocities or the degrees to which they exploded into. We're only looking for speeds. We don't have to worry about any vectors. Now we know our formula. We know our formula is MA plus MB VI, and here actually we have MC, so plus MC VI, 5.4 meters per second, equals MAVA plus MBVB plus MCVC, and we have to find what MC is. So here we're just going through some simple algebra here. First, do not substitute any values in yet. We want to simplify this down before we substitute any values in. So if we multiply the VI into the different variables, we have MAVI plus MBVI plus MCVI equals the same thing over here, MAVA plus MBVB plus MCVC, and now we can put these two on the same side. So we could say, we simply rearrange everything. So then we can have MAV1 minus MAVA plus MBVI minus MBVB equals MCVC minus MCVI. Driving part, and this really isn't necessary, so if you want to learn how to do this, stick around and I'll show you. But really, this would be the end of what you need to know, what you need to learn for momentum and impulse. So if you have any questions, our Instagrams are up here. I don't think we're going to change our handles anytime soon anyway, so just shoot us here. And yeah, if you guys need any help, of course, comment below. If you have any requests for units or different subject areas, comment and we'll see if we can do it. How we derive this, let's take a look. So F equals ma, we know, is known as the formula for Newton's second law, which deals with the acceleration of mass due to an applied force, and originally Newton wrote it as F equals the change in momentum, the impulse, over a change in time. So let's see how we can derive F equals ma from the original equation, from this equation, using our other smaller general physics equations. So if we have F equals a change in P over a change in T, we need to look for mass and acceleration when we know that change in P, our impulse, is mass times the change in velocity, and time is part of the acceleration formula. And really it's, let me write this in the original form first. Acceleration equals change in velocity over time. And it should be quite intuitive now. We have force equals m, the change in velocity, over a change in time, change of velocity over change in time, which means we can rewrite this as mass times acceleration. And there you go. We just basically derived Newton's second law from his original momentum and time law. So I hope you enjoyed this little bonus, and I hope you guys enjoy this video. I hope it was clear enough. We try to keep these as condensed as possible so you can learn it in a quick bite at a time. Okay, awesome. And we'll see you guys next time. I'll bring this page up again. See you guys next time.